We are in the home stretch. We're rounding third on our way to home. Everybody's cheering. Grand Slam. I don't know. That was from bad baseball metaphors aside. All right, so let's take this idea of orthogonal projections and we're going to look at a couple of theorems. And excuse you? Excuse you. Okay. So if W is a subspace, then each vector in R2 or Rn can be written in a unique form where we can break that vector down into its orthogonal component, into those two orthogonal pieces. And the nice thing about this is that it makes it is this idea of uniqueness. Now, this can only be done as long as we have an orthogonal basis for W. So if orthogonal is our basis for W, then our y hat is just the linear combination of those bases that get us y. Oops. Yeah, okay. So what this means, okay, so let's try this again. So y here, y hat is the constants. So these are the constants that would make up the linear combinations of y. And add them together and we get our y hat. Yeah, 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 yeah. And then z again is y minus y hat. So picture-wise, so now we're not just talking about maybe projecting onto a single plane or a single line. Now we're talking about our projections being onto a subspace. So the any other thing in the space projected onto the subspace is what we're talking about here. Oh, hey, I did not finish this example. Isn't that lovely? All right, let's fill these in. Okay, filled those in for myself. Don't worry, I fixed your notes. It will actually exist in yours, but I don't know, it was fun. It was exciting. Okay, so if W is the span of U1 and U2, we want to be able to write Y as a sum of a vector in W and a vector in W perp. So the vector in W is what happens when I get my Y hat. And the vector in Y perp is my Z vector. So this would be Z. This one is Y hat. Other than that hat, different hat, that hat. Now, first, in order for us to actually do this orthogonal decomposition theorem, we need to make sure that our set here, our spanning set, is an orthogonal basis for W. So we've defined W to be the span of U1 and U2. And in order for it to be an orthogonal basis, we need to make sure that these two things are orthogonal to each other. So all we need to do is first we need to check and make sure that the dot product of U1 and U2 is 0. So it'd be 2 times, so negative 4 plus 5 minus 1 absolutely gives me 0. So we're all good there. We are perpendicular. So this is an orthogonal basis for W. Okay. Now we can go forward with this nonsense. So we're going to find our y hat. So our y hat we find by taking y. So we're going to have two of these. So we're going to have y times u1, or dotted with u1 over u1 dotted with itself times the vector u1. Ugh, that's not a... Okay, stop doing that, dingus. That's me. All right, these are all vectors, but you get the point. Oh, also, this guy. Ooh. Okay, it's been a long summer already. Yeah, it's been a long summer for me. Okay, and then we're going to do the same thing, but this time we're going to take y and u2. And then u2 with itself. And that. Okay, so our result here is going to be a vector. Yay, vectors. Okay, we're going to take, so we'd have y times u1. So 1 times 2 is 2, 2 times 5 is 10, 3 times -1 is -3, over 4 plus 25 plus 1 times the vector 2, 5, -1. All right, we'll come back and simplify this as soon as we're, no, wrong hat. After we get this all down. Also, the dog is prancing, so in a minute I will have to go talk to her and deal with it. Okay, y dotted with u2, so now we have 1 times -2 is -2. 1 times 2 is 2, 1 times 3 is 3, over 4 plus 1 plus 1. Again, I'm squaring each of the components of u2 in order to get my dot product for u and u. And this is going to be multiplied by the 2, 1, 1 vector. All right, so 12, 10, 9. So it's 9 over 30 times the vector 2, 5, -1. And that's 3 over 8. No, 6. 3 over 6 times the vector -2, 1, 1. Movie magic. You ready? Ta-da! No? Okay. Movie magic is going to say, it's going to appear before you know it. You guys don't even want to know how long I struggled with that. I refused to get a calculator out, and that's what happened. All right, so here's our y hat. Again, all I did was I did some simplifying. I multiplied, I added. The last thing we want to find, so there's our y hat, so we want to find z, and we know that z is y minus y hat. Y hat. Everybody's wearing hats. So that's 1, 2, 3 minus our -2/5, 2 and 1/5 gives us 5 is 7/5. 7/5 there. 2 minus 2 is 0, and 3 minus a fifth. So that's 15/5, 14/5 there. Okay, something like that. And hopefully we could graph these, we could double check, but we're hoping that these two things are perpendicular. We could double check by taking their dot product and making sure. I'm assuming that we're going to end up with, so -14 25ths, 14 25ths, and then this one's a positive 14 25ths. Oh, hey, that's 0. So yes, these two things are perpendicular to each other, and it's a wonderful time. Yep. Okay. I had a great time. Last little bit here. This last theorem is kind of intuitive, I think, but maybe not. And the reason we use this, so it's called the best approximation theorem because sometimes we need our vector to be in our subspace, but it's not in our subspace. So we use the best approximation of it, and the best approximation of y in our subspace is the orthogonal projection of y into our subspace. Right? So if we think about it, so here's y, why not? Here's my subspace W. In this case, I'm going to let it be a line. And the closest I can get is that this would be, so my y hat needs to be in W, whereas y doesn't have to be in W. Y is some other vector in the larger vector space. And W is some subspace of that. So sometimes I want to deal with something that's in my subspace, but I can't. So like y may not actually exist in my subspace. And if it doesn't, then the closest I can get, or the closest in length, and or the closest sort of approximation of my y vector is my orthogonal projection. Kind of makes sense. This last one says that if y is in W, so if y is already in, so here's a different y, here's y2, why not? If it's already in my W, then if I try to project this, I can't go anywhere. I'm already on that particular subspace. I'm already in that subspace, so there is no projection, which means that our y hat is equal to y. which means that our z, our perpendicular vector, is the 0 vector, so it's trivial. All right, that's it. That's all she wrote. We're done. Yay!